In this session, we will discuss about Chandy-Misra-Haas algorithm, which is a deadlock detection algorithm. In this algorithm, the processes are allowed to request multiple resources at once, instead of one at a time. So by allowing multiple requests simultaneously, the growing phase of a transaction can be speeded up considerably. So the consequences of this change to the model is that a process may now wait on two or more resources simultaneously. We will try to understand this algorithm with the help of a resource graph. Now here we have three machines, machine 0, machine 1 and machine 2. On machine 0, there are three processes. We are not showing the resources. Here also there are three processes, and on machine 2 also there are three processes. Now on machine 0, some of the processes are waiting for local resources, such as process 1 is waiting for resources which are held by process 2 on machine 0. Whereas on machine 1, we can see that process 3 is waiting for some resources which are held by process number 4 and process number 5. Whereas on machine 2, process number 6 is waiting for some resources which are held by process number 8. So this is about the local processes on each machine. But there are some other processes on each machine which are waiting for resources on some other machine. Like process 2 is waiting for a resource on process number 3, which is on a different machine, that is, it is on machine 1. Similarly, 4 is waiting for some resources which are held by 6 on machine 2. So the Chandy-Misra-Haas algorithm is invoked when a process has to wait for some resources. As we have seen in our example, process 0 was blocking on process 1. So in this case, the Chandy-Misra-Haas algorithm would be invoked. Now when this algorithm is invoked, a special message which is called as the probe message is generated. And this is sent to the process holding the needed resources. Now this probe message consists of three numbers. Now what are these three numbers? The first number is the process that has blocked. The second number, so this is our first number. The second number is the process sending the message. And the third number is the process to whom it is being sent. So in our case, the initial message from 0 to 1 will contain this probe message, that is 0, 0 and 1. So why is it 0, 0, 1 is because the first parameter is that the process that has just blocked. The second parameter over here is the process sending the message, because the message is sent by process 0, and the third parameter is the process to whom it is being sent. So the probe message was sent from 0 to 1. So here is the probe message. We have three parameters in the probe message: the first parameter, second and the third. So the first parameter refers to the process that just blocked. The second parameter refers to the process sending the message, and the third parameter refers to the process to whom it is being sent. Now when the message arrives, the recipient checks to see if it itself is waiting for any other processes. So if it is waiting for some other process, there will be a modification in the probe message. So what I mean with respect to this is, on machine 1 we have 3 processes: process 0, process 1 and process 2. We have seen in the resource graph that 0 was waiting for a resource which are held by 1, and 1 is waiting for some resources which are held by 2. Now initially there was a probe message which was sent by 0 to 1. So it had 3 parameters. The first parameter was the process that just blocked. So since 0 is waiting for resources held on 1, so the first parameter would be 0. The second parameter is the process sending the message. Now which process is sending the message? 0 itself is sending the message, so here it will be 0. And the third parameter is the process to whom it is being sent. Okay, so the message was being sent to process 1, so the probe message was 1 in this case. Now when the message arrived at the recipient, now this is the recipient here in this case, it checks to see if it is itself waiting for any other process. Now in this case 1 is waiting for some resources held by process 2. So in this case what we do is we keep the first field as the same. So now the probe message from 1 to 2 would be 0, replacing the second field by its own process number. So instead of keeping it as 0, we will replace this by 1. And the third parameter is the number of the process it is waiting for. So in this case it is waiting for process 2 to release the resources. So now the probe message would be something like this. So 0, 1 and 2. The message is then sent to the process on which it is blocked. So now in this case, if it is blocked on multiple processes, all of them are sent some different messages. So now what happens is, if a message goes all the way around and comes back to the original sender, that is the process listed in the first field. That means the initial blocking process was done by 0, and if it goes through an entire process and comes back to 0, that means a cycle exists, and in that case a system is deadlock. We'll go through this example. So we see machine 0, 0 waiting for 1, 1 waiting for 2, and 2 is waiting for 3 on the next machine. So now here the 3 parameters will be 0, 0, 1. 0 is the 1. The first parameter is the process that has just blocked, since it is waiting for resources from 1. Next parameter in this case is the process which is sending the message. So in this case it is 0, and the message is being sent to 1. So the third parameter is the process to whom it is being sent. So the probe message in this case would be 0, 0, 1. Whereas in case of the next from 1 to 2, so we will have 0 as it is, 1 and 2. Right? So we have 0, 1 and 2. Now the message moves from machine 0 to machine 1. So in this case also it will remain the same. So the initial blocking process will remain the same. So initial blocking process over here is 0. Process sending the message is 2, and the message is being sent to 3. So this will be the probe message from 2 to 3. Next, the message is being sent from 3 to 4 on the local machine 1. So we keep the first parameter as it is. The process which is sending the message is 3, and the message is being sent to 4. Similarly, from 4 it moves to 6. So the first parameter remains the same. Message is being sent by 4, and receiving process is 6 on machine 2. So the probe message in this case is 0, 4, 6. The same message is being sent to 8 because 6 is waiting for resources which are held by process 8. So in this case the first parameter remains the same. Process that is sending a message is 6, and the process to whom it is being sent is 8 in this case. and 8 is waiting for some resources which are held by process 0 on machine 0. So we can see over here the first parameter remains the same, the process that blocked, the process that is sending the message, that is 8, and the third parameter over here is the process to whom it is being sent. So it is being sent to the original process on machine 0 which initiated this probe message. So now in this case what happens is there is a cycle, okay, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 4 to 6, 6 to 8 and 8 to 0. There is a cycle. So now when there is a cycle in the system, we say that the system is in a deadlock state. So this is how we detect a deadlock using the Chandy-Misra-Haas algorithm. Now there are various other ways in which the deadlock can be broken. One of the simplest way to break this deadlock is we make the process that initiated the probe to commit suicide. But this particular method of committing suicide has several other problems. For example, what can happen is, in case process 0 and process 6 block at the same moment and both initiate the probe messages. So what would happen in this case is both these processes will eventually discover that there is a deadlock and both will try to kill itself. So this will cause an overkill. So we do not want more than one process to commit suicide. It is just sufficient for one process to kill. So this is how the Chandy-Misra-Haas algorithm works.